Next segment, second law of motion. Okay, so second law of motion is the relationship that really is kind of the key relationship to all of the laws of motion. Okay, it's the one that gives us our equation, and now it's a new equation on our board, so it's the next one in our order. It's F equals ma. When we start talking about this, again, we're looking at this F. This is our force. The m is the mass of the object, and the a is the acceleration. So what Newton was getting at is this. He said that if an object has acceleration, okay, if we see the velocities changing, the reason that happens is because there was some kind of a force that was applied, okay? So in the first law of motion, it was an object at rest stays at rest, object in motion stays in motion. In other words, all the forces were balanced. So there was no motion or no force that was applied to make a change there. Now, if we do apply a force to a balanced situation, all of a sudden we become unbalanced in our forces. So we have unbalanced forces, and it's the net force that causes us to do that acceleration. And the acceleration happens in the direction of the where the object is. So again, if I go back to a marker being tossed in the air, because I think I've been tossing markers in the air a lot. So if I take this marker and I throw it in the air, it gains this motion due to me applying the force. And then its motion starts to slow down due to the force of gravity. So we're going to actually equate gravity now actually into a force, not into just a form of acceleration. And so that's kind of where we start with this whole process, as we look at the relationship that a force has to the mass and to the acceleration. In ninth grade science, okay, again, I like to refer back to the definition or way we talked about it in ninth grade. It was if we wanted to accelerate an object, we needed to have a force. So if you want to see something accelerate, you have to apply force to it. So let's look at this in terms of what happens. So here I have the green ball here. It represents having a constant mass. Okay, so the mass stays the same, and I look at the amount of force I have relative to the acceleration that is produced. So if I have a big force, I get big acceleration. If I have a little force, I get little acceleration. So the size of our arrows translate between our two different vector quantities. So force is a vector, acceleration is a vector, mass is a scalar. Okay, so that's how we kind of relate that. If we look at another relationship, so let's take a look at a different relationship. I need to erase my marks here. Okay, so now what we're going to do is we're going to hold the force constant. So in other words, if we maintain the force, so in other words, sounds like a Jedi talk. Okay, if I maintain the force, so I keep the same force through all of my motion, okay, so I'm swinging my golf club. If I hit the golf ball, which has a very little mass, okay, small mass, I get big acceleration, okay, because there's that relationship. If I use the exact same force on a big mass, I'm going to get very, very small acceleration, okay? So the same force, when we have small mass, we get big acceleration. When we use the same force, if we have big mass, we get small acceleration. You can see that kind of a relationship is an inverse relationship. So the relationship between mass and acceleration is inversely proportional to each other. Okay? And now let's look at our last situation here. Okay, so we talked about mass being held constant. Oh, if the acceleration is held constant, okay, that's a direct relationship. So in other words, if I accelerate an object, the bigger the mass, okay, the less force. It's an inverse relationship as well. Okay, I think that makes sense. I might have to talk about that one in class a little bit. I noticed I didn't have a nice picture for that one. All right, so when we talk forces, we have to look at it in terms of units. So if you remember, mass was in kilograms, okay? Acceleration was in meters per second squared. So when we mush the two together, we get kilograms meters per second squared. So kilograms meters per second squared, kilograms meters per second squared, kilograms meters per second squared. So what's a Newton? A Newton is 1 kilogram meter per second squared. Now they got tired of saying kilograms meters per second squared all the time, so they just said, let's call it a Newton. So 1 Newton is equivalent to 1 kilogram meter per second squared. This relates directly back to that stuff from the very first topic set when we said everything can be broke down into its fundamentals. So the fundamental was mass, length, and time that we used to make our force. So force is a derived quantity based upon those. When we start to look at forces, we like to start diagramming our forces and all the forces that are playing a role in something. So let's just say that I have a box, okay, and I want to push this box. And so I'm going to push this box with some force, okay, so this is me pushing a force, and the box then is going to move because there's nothing to balance it. Well, you might say that the box has weight, so there's a force due to gravity that's acting on it. Well, and right now I don't have anything, I need to have a surface, so if I have a surface that I'm on, the surface provides a force up, so there's an upward force that balances this, and the size of this arrow and the size of this arrow are going to be in equilibrium because we're saying an object at rest stays at rest, okay, if the forces are balanced. So in other words, the force up and the force down are balanced. My unbalanced force is this force that I'm pushing with, so the object then moves this way. And we do this in something that we call a free body diagram, okay? Free body diagrams are this. There's something that has a point. Point represents kind of the, let me move my point down here. The point represents the kind of center of mass or the center of gravity for an object, so all objects have a center of gravity. And then we just draw arrows away from our center of gravity and we start to label those arrows. And so there's my two arrows saying that the object's not moving up or down, okay, because those forces are balanced. And here's my arrow representing me pushing the box, and that would be the unbalanced force. And we call this thing, again, a free body diagram. There is a net force, and the net force then tells us what kind of acceleration we're going to produce. So this net force produces some acceleration if I know the mass. So like if my Hot Wheels car is traveling on a track, it's traveling that way, and so then I can see that how much it's going to accelerate by, and so where is it going to end up. And so that's how we're going to tie that into kind of problems, is looking at it in terms of where's the net force, okay? And this is what we like to talk is net force. So where's the net force in relation to all of the other forces, okay? One comment about center of gravity, again, all objects do have a center of gravity. And if I look at like a ruler, I can look at this dimension and I can see that it balances there. So the center of gravity is about right there, okay? And it doesn't make any difference. If I turn it this way and I can balance it on my finger this way, as long as I put a supporting force through the center of gravity, I can kind of keep it at equilibrium, okay? And so that's kind of what we're doing in Newton's second law of motion. This is our big concept, last big concept. So like this arrow right here was the arrow that was acted due to gravity, okay? And so when we start to apply gravity to a mass, okay, a mass times gravity, that's what we call weight, okay? That's weight. And weight is a force. It is a force. We generally measure it in newtons, so that's something that we need to make sure that we're looking at. So F equals ma. If A is gravity, then our force is our weight. Okay? So again, that's one of those things that we tried to teach you in 9th grade science, that mass and weight are not the same thing, okay? Mass is a fundamental quantity, weight is a derived quantity due to the fact that it's a force. And that should be the end of my stuff for second law of motion, so we will pause here, maybe, and then we'll start with third law of motion next.